One of the weirdest predictions of quantum mechanics, or strangest ideas that's used in quantum mechanics, is this idea that matter actually behaves like a wave, just like light behaves like a particle. So not only do photons have this wave-particle duality that we've talked about, but matter does too. For most things that we observe in our everyday lives, this doesn't actually affect us. The wave properties of like a baseball or a person really are not noticeable or measurable even. But when we're talking about things as small as electrons and atoms and molecules, we can actually observe this. This was postulated by a French physicist named de Broglie. I'm sure you're supposed to pronounce it differently, but I do not speak French, so it might be like de Broglie or something. But I don't actually speak French, so we'll call it de Broglie. In the early 1900s, when all of these other discoveries were happening, it was an interesting time to be alive in terms of if you were a physicist. There were lots of exciting things happening. De Broglie said, well, if photons, right, if light that we think of as a wave mostly can behave like a particle, what about an electron or any other particle for that matter? This is not limited to electrons. What if that thing that we think of as having like a certain mass, certain like size or whatever, what if it can behave like a wave? And de Broglie came up with this equation where we can actually predict the wavelength associated with a moving particle. So he said that the wavelength, and again, this is similar to the idea of wavelength of light that we're talking about, except for now we're not talking about light. We're talking about like chunks of matter, right? Electrons, protons, atoms, molecules. The wavelength associated with that is equal to Planck's constant divided by m times, let me use the same variable that your textbook uses, u. Here, this is the speed of the particle, and this is the mass of the particle. And then h here is the same constant we've seen a few times now, which is called Planck's constant. Again, which Planck came up with to explain blackbody radiation. This constant shows up all over the place in science now. So basically, what we can say is that if we have an electron, we can think of it as behaving like a wave and having a wavelength that we can calculate. Now, what does this have to do with the Bohr model? Well, if instead of thinking of a electron as a particle traveling in orbits around a positively charged nucleus, we think of electron as a wave, sort of waving around the nucleus. Then we can explain why it only takes certain values, why it's quantized, why you can only have n equals 1, n equals 2, n equals 3, etc. And I'll try and draw this. It's a little bit tricky to draw this, but if we have, we'll think about a string like a violin string. If we have a wave that's sort of fixed on two ends, we can fit only certain numbers of wavelengths between those two ends. If the ends are stuck on the wall or stuck to something at a certain point. This is what happens in guitars and any violins, any string instruments, is that the string is stuck at a certain point, but it can resonate at different frequencies. So we can have one like this, or we could have one like this. And the same thing is happening, according to de Broglie, inside of the electron. This would represent like our n equals 1 wave, or n equals 1 electron wave. This would be our n equals 2 electron wave. And then n equals 3 would look something like this. We go up. Okay, let me try and draw this. Up, down. You need two ups, like there. There we go. The key here being that we have what are called nodes here at the end, where the wave has to be 0 there. We end up with nodes in the middle here, and two nodes here. These are what we call standing waves. Now you can imagine taking these waves and then wrapping them around a circle. And this is the part that's hard to draw, but I'll try my best. But we can imagine we have our nucleus here, and then our wave, our electron wave, is going. So if let me use a different color. So if this sort of represents the plane of the electron, so we can have a wave. All right, let's try this again. So just to represent sort of an even surface here. So if our wave starts here, it can go up and then come back down. Sorry, that's not. Go up and down and then back up. So I'm trying to draw this as like taking this sine wave here and wrapping it around in a circle. And what we need is that we get nodes on both sides that match up with each other. Otherwise, it's not stable and the electron can't stay there. So if this is a little bit tricky, I understand. But this was the idea. And this idea of electrons having a wavelength was really revolutionary at the time. I was reading about a little bit of history of de Broglie. He proposed this in his PhD thesis, of all places. And his advisors that were, assessing his thesis thought like he's a little bit crazy. Like, we're not quite sure if this makes any sense. So they actually sent his thesis to Albert Einstein to have him, in Germany to give his opinion on it. And he said, "Oh, this looks very promising." And so that was enough. That was an endorsement for de Broglie, and he passed his his dissertation, his thesis, and got his PhD. So that was a pretty good endorsement. And it turns out he's right. Matter does behave like waves, and so we can use electrons, use their wave-like properties to actually observe. And we've even observed this with things as large as like 60 atoms or molecules like that. So this is one property of matter that's a little bit weird, but quantum mechanics predicts it, and it lines up with the experimental observations. So while this may seem strange, it really happens. So quantum mechanics is just a little bit weird like that. One consequence of the wave nature of particles, the wave nature of things like electrons, is what's known as the uncertainty principle. You may or may not have heard of this before, but this is due to the fact that matter behaves like waves. And it is that there is some uncertainty, just like with any waves, we can't really point to an exact location. So it's an uncertainty with regard to position meaning where a particle is, and momentum, which is how fast is it going. Because of the wave nature of particles, we can't know both of these precisely at the same time. And so there's this relationship that's delta x times delta p, p is momentum, is greater than or equal to h over 4 pi. Or in your book it writes it this way, delta x times m delta u, which is the same. This is delta p. You might see it either way, is equal to h over 4 pi. What does this mean? It means if we precisely know the position, x represents position here, if delta x is 0, meaning we know exactly where a particle is, it means we have no idea, to satisfy this inequality, this has to be infinite. We have no idea how fast the particle is moving. And vice versa, if we know exactly how fast a particle is moving, we have no idea where it is. And this is due to the wave nature of particles, of matter, I should say. And there's a limit to how well, if we know one to a certain amount, we can only know the other one to a certain amount. So this is just one of those funny things with quantum mechanics. When we're thinking about things on the very, very small scale, they're waves. They have this particle and wave nature, just like light does, and we can't know everything about them. And that's actually part of the reason why Bohr's model doesn't work. If we think about Bohr's model of electrons orbiting around, and we could say it's a wave. If we know it's orbiting around, we know how fast it's going and we know where it is. But that violates the uncertainty principle. So this model is not 100% correct. The idea of energy levels within it is correct. The electron can only occupy certain energy levels, but it's not circles. Even though we like to draw pictures of the atom, you might often see things like this. We use this to represent atoms, and that's sort of Bohr's model. This isn't actually what atoms look like. Sorry. But we all, that's still the symbol that's commonly used in pop culture. So what does that mean? So if this is not the right model, what is the right model? We'll get into that in the next video.